Hello and welcome back to Calculus 3. We are starting chapter 17 on vector calculus. So 17.1 on vector fields. This is going to be the basic idea. This chapter is going to bring everything we learned in the whole course so far together. We are going to use concepts from every chapter, including chapter 12 from Calc 2, and then obviously basic differentiation, integration, and everything else. So technically everything you ever learned in calculus converges in this chapter. The vector fields are extremely important in sciences, primarily physics, obviously, which is the basic for everything else. If you are talking about gravity, you are going to talk about gravitational field. You are going to talk also about electric field, magnetic field. And then you will realize there are things like currents in the water. There are winds and hurricanes and tornadoes. And you can put the fan on and sit in front of it. Not on a terribly hot day, but on a day like this, maybe the fan would do some good. Otherwise, it just acts as, as a device that makes it worse. So, what is the vector field? Please imagine the air in this room and think of every individual molecule which is moving through this room. Now, pick a position, starting position for that molecule of air and attach a vector to it which will show with its direction, right, the way the molecule would move and with its magnitude of how fast that molecule moves through space. And now, because there are billions upon billions of air molecules in this room, you are going to imagine that when they all line up, not all, but a lot of them line up, you will feel a breeze as they move. So if you take a look at some science books, you will simply see that water, wind, and electricity, they all work on the same principle, which is difference of potential. If you have a difference of potential, in terms of electricity, you are going to have flow of electricity, you get electrical current, which is why you always need a plus or minus, or you need a hot and a neutral, and so on. If you are talking about the wind, you are going to have a higher pressure and the area with lower pressure, and then the air is going to move and create the wind. You are also going to have the same thing happen with the currents in the ocean, and so and so and so. So, or it's easier to think of the water running down the hill. The water that is higher up has higher potential energy than the one right then when it goes down, because all objects want to have the lowest energy possible. Water will flow downhill to get to that lower energy state. Everything on this planet, every single molecule, atom of this planet is trying to be as close as possible to the center of the planet, which is why the planet is round. So we use these vector fields to describe mathematically the framework in which the gravity, electrical, magnetic, and all other fields in which they work. And then by observing the vectors, and remember our first lecture was on vectors, and I said that day one, vectors do not exist. They are mathematical abstraction and mathematical constructs for us to understand things better and easier. So you are now imagining billions upon billions upon billions of these little tiny vectors that are creating these fields in which molecules, atoms, and so on will move. The big scope example for you to, and this would be the last one, would be the flow of traffic. If you take a look, let's say you take a look at the New York grid or something where, each avenues have both ways, most of them, I think, and then the streets are, most of them are, or all of them, I'm not sure, are one way. So you will have all of the vectors go one way on the other place, where everyone will be going the other way, and in some places they will be going two-way, but again, not in the same lane. So now we would like to start with defining the vector field, and then just going to take a look at few simple calculations. So it's very short. So we are starting with definition of vector field in 2 dimensions, so in R squared. So we'll say let F and G be defined on a region R in R2, a vector field in the future denoted as VF, a vector field in R2, there will be another one for R3, is a function, and guys, we are using capital F with the arrow on top. You will distinguish between the vectors which have lowercase, single vector, and vector fields which consist of billions or infinite many, right, by capital F. So, vector field is a function that assigns to each point of R a vector, and this is where those functions come in. So now we have f of xy and g of xy. Notation is vector field xy is given as the vector of fxy, gxy, or you can use ij notation, component 1, so fxy is equal to fxy I with a hat plus gxy, the j with a hat. So these are the ones. A little side note over here. This is also given as another part of the definition. If f and g are continuous and differentiable on R, then vector field F is continuous and differentiable on R. So this is what you have as a vector field. And guys, this stuff is extremely easy. You get some kind of a vector field given. Say you have 2xy and then 1 over x, for instance. And as you can see, x is not allowed to be 0 because it would create undefined piece for the g spot over here. But let's go and take a look at, let's say you pick a point 3, 1. If you pick a point 3, 1, then that would create a vector at 3, 1, which is you simply plug in 3 and 1, and you get 6, 1 as a vector. And you can graph that one. So that will be, you're thinking of the single particle that sits somewhere in this room at 3, 1, and then 6, 1 would be its direction in which it goes. You can pick a value, let's say you pick 2 1/2. If you pick 2 1/2, then the vector field computed at 2 1/2 will give you a vector. When you plug in 2 1/2, that cancels to 1 times 2 is 2, and then 1 divided by half is 2, so we will get 2, 2 as a vector. So simply, these over here are points, x, y, and we plug them in to obtain vector. So if you're trying to understand this, I will just say that vector field, so VF, is a function which generates all vectors in its domain, and I'll put AB so we know that's a point AB that you can. So again, the previous example, we have to exclude all of the points that would have x equals 0. So you are not allowed to plug in anything from y-axis. So that one would not be generating any. Now we do have some cool vector fields to consider. So one of the cool vector fields to consider is called radial vector field. And that one is denoted with F equals, and I'll just put X and a Y. So if you have a radial vector field, this one would look like, you know, when the kids draw the sun, so they draw the little face with a smiley, and then they put these rays going out like that. That's actually, those are the infant stages of drawing the radial vector field. So you all know how to draw a two-dimensional vector field. You knew that since you were 4. All right? Now we can actually do a little bit better job because you are no longer 4. You will pick points, and then you will calculate the vectors. So let's say you pick a point 0, 0. If you pick a point 0, 0, vector computed at 0, 0, vector field computed at 0, 0 will yield vector 0, 0, and that's just the origin. So nothing special is going on for 0, 0. We'll just put the x and y coordinate system here, and I'll put a big fat dot in at the origin. That's our 0. Let's say you have 1, 1, 0. So if you have 1, 0, then vector field at 1, 0 will be vector 1, 0. And to draw that one, let's say this is our unit 1. Over here, 2 squares, 1, 2, 3. So you are going to have a vector that stretches 1 unit in length from the origin outwards. Similarly, if you have, let's say, 0, 1, which is on the y-axis, then f of 0, 1 would be a vector 0, 1, because this is, again, x, y, so whatever point you have is technically the vector you're looking at, and then that one would go up. If you happen to have a point 2, 2, then, oh, oops. I'm drawing this wrong. Yes, vectors are free to move in space, but they should, for vector fields, if this is the point at which the vector is drawn, vector is here. There we go. And vector is here. So not this one. Much better. So let's use 1, 1, it's easier. If I do 1, 1, so f of 1, 1 will be the vector 1, 1. So we go to the point 1, 1, and we draw a vector 1, 1, so this way. So you see what happens if I continue this pattern everywhere. You get this vector field that shines out, right? Looks like there was an explosion in the middle and it just goes in all directions around. It's called radial field, and you will see it a lot. So that's the one to remember. Another good field to remember would be rotational field. Rotational vector field, so rotational VF, given by the formula y negative x or negative yx or whatever. Rotational field. Again, point 0, 0 will generate a vector at 0, 0, which is just 0, 0. So nothing special going on. Big fat dot in the middle of the coordinate system. It's a 0 vector. But then when you go 1, 0 as a point, then the vector field of 1, 0 will create. Now look, your x is 1, so that's going to become a negative 1, and then this one is 0. So you have to go to 1, 0, which is here, and draw the vector downwards. That would be a 0, negative 1 vector, because it goes 0 in x and negative 1 in y, so it goes down. You have to do that at the point 1. Then let's say you have 0, 1. So vector at 0, 1 would be 1, 0. So 0, 1, 1, 0 would be this vector here at the value of 1. Let's go with negative 1, 0. Negative 1, 0. It will be 0, 1. So negative 1, 0 is here. And then we go 0 in x, 1 in y. It goes up. And then if you continue the pattern, it will go like this. And then at 2 would make larger like this. And as you can see, it has the spin to it. Now, it's if you go and calculate at any point on a diagonal, let's say you want to calculate at 1, 1. F at 1, 1 would be 1, negative 1. So that one I'm going to just do the blue. So we go at 1, 1. We have to go 1 unit to the right and 1 unit down. It would be this vector like right here. So in general, I hope you guys can see that it's a spin around the origin. So all of these vectors will be pushing. Rotational vector fields. There are a lot of vector fields. Those of you going into electrical engineering, you learn about eddy currents, which are pain of your existence because they are the ones that will be destroying the efficiency of your devices. You want to avoid them at every point, which is why the most efficient chargers that we have today are the ones that using torus as a transformer, not the blocks anymore, because the blocks actually have a lot of inducted eddy currents and so on. So there's a lot of application for these rotational vector fields. Obviously, you can talk about hurricanes, tornadoes, and other things. They all have this in the base. Some other examples would be a shear field. Given as 0x. And that one would create on one side vectors that go up, and the further out you are, the stronger the movement. On the other side, you have the small ones going like so, and then a little bit longer. And you can obviously play with points. So that's the shear field. And then the nice one is the channel flow. Which is given by, in this case, now obviously you can swap x and y's and stuff like that. So 1 minus y squared 0, which will create a flow like this. So the longest vectors would be in the middle, and then the shorter vectors would go on either side, and then the shorter vectors still would go here, and the very short vectors, oops. And when you get all the way, because it's a 1 over here, when you go up to y equals 1, they disappear. So you see that these, all of this is really good for explaining the flow, because the flow through the, you can think of this as radial now, the flow through the garden hose, let's say, or the blood vessels, is strongest in the middle, because there is no friction of liquid rubbing against the walls of the vessel that the liquid flows through. So the closer it is to the wall, the more friction it has, and it slows down the flow. So this is a two-dimensional representation. Obviously, three-dimensional representation would have two components that look like this, and then 0 on the third component, which would be also determining which way this is all oriented. So practicing a little bit about these vector fields, you would do well. And now, vector fields in R3. It's the same. I'll just put over here definition. Same as R2, but in R3 notation. So you are getting the same idea. So I'm just going to write the notation. So f of x, y, z is going to be f x, y, z, g x, y, z, and age x, y, z. Or you can use it in the component form, which is f of x, y, z, I with a hat, plus g x, y, z, j with a hat, plus age x, y, z, k with a hat. Examples are calculated exactly the same way. So if you have a vector field x, y, z given as, let's say, x, y, 1 minus y, and x, z squared, let's say. if the point in 3D is given to you, you can calculate the 3D vector associated to that point, which technically shows which way the point goes. So if you have, let's say, 3, 2, 1 as a point, then the vector field at 3, 2, 1 will produce a single vector, x and y. X times y, that's a 6. Y, 1 minus 2, negative 1. And x z squared, z is 1, so 3. Vector fields take point as the input, and they spit out a vector. And that vector is supposed to represent the way, the direction in which the point wants to move. So 2D, 3D example, all good. You have x, y, z, plug them in, and compute the vector field. The last thing for this section, before we take a look at some pretty pictures, is going to be the definition which allows us to get these vector fields. And this is gradient fields and potential function. So we say let phi be differentiable on a region of R2 or R3s. This works for any dimensional space. If you want 16 dimensions, go ahead. It's just going to have 16 parts in a vector. So the vector field F equals del phi is a gradient field, and the function phi is a potential function for f. So let phi be differentiable on a region. So guys, this is just, if you have, well, anytime you found the gradient, remember you found the gradient for directional vector, you found the gradient for Lagrange, every single one of those gradients that you got was a vector field. Potential function generates the vector field. So if you have some kind of a function, you can generate a vector field using that function, which is why we have technology we have today. It is well understood that electrical devices create electrical field. There is a duality between electrical and magnetic field. You can turn one into another very easily. We just add the motion. So if you have a movement of a wire through the magnetic field, you induct electricity. If you put the electricity, alternating electricity, not the direct one from the battery, into a wire, you can create magnetic field and so on. When I was in high school, this was, I believe, we were first year. Yeah, first year I created with my friends a little zap device for handshakes, and it was really cool. So you can step up the voltage from the 9-volt battery. You bake a little circuit that will interrupt and switch polarity off of the battery, and then just run 2 wires through the sweater and a little 2 poles on your, and then when you shake hand with someone, it was really cool. Obviously, the current on that is next to nothing, and it's alternating currents, so it's not life-threatening, but it does pack a nice little punch. It feels like being I don't know, poked with a needle or something in the hand. So it wasn't pleasant at all, but it was a lot of fun. So you can make these kind of things very, very easily. The little flashlights, and especially today with diodes, when we used to make these things, it was terrible because all we had were conventional car light bulbs, and those were not, right? So you can make these things into devices that you guys can have fun with, or they can have actually purpose and use. So I don't know, design other things. So that's the vector fields. Just to take a look at some of the pretty pictures from your textbook. Let me see, where are the... Oh, there they are. So what you are looking here at is some kind of hurricane, and you can see the vector field of rotation. Then there is stuff going up, there's stuff rotating. So the way the science is done, and that's 17.3. If I can get it to it today, we'll talk about it, most likely not. The way the science is done is you can measure fields, all right? We have devices that can measure the field. And then if that field is conservative, and we'll learn what that means in 17.3, if that field is conservative, then there is a procedure that you can use to come up with a function, potential function, which generated that field. This is how we understand science. So what you do is well, not you, whoever is stupid enough to drive up to a tornado or a hurricane and toss little sensors that will be picked up by these high winds and transmit back the data in terms of the direction and velocity and position of those objects. Then when you are receiving that data, you are receiving the data which is the vector field data, because you have the position of where the individual particles are. You model that into a vector field model, which is something that you've already seen in this lecture, and then use 17.3 later to transform that particular field back into the good old equation that you all know. And then you have physics. After that, you can go on with engineering and create devices. So obviously, mathematics has to define these terms first, then physics figures out how that plays the role in the natural world, and then engineering, I don't know, 100, 200 years later, comes up with the devices that would use those principles, and then we have cool toys. So let's say that the function phi of x, y, z is given as just stuff that you guys know, 3x squared z minus 3x squared z minus 4 ln xy, whatever, right? So let's say that's the function. You have seen these functions. We used f so far. Now we're switching to phi because we want to we keep f for our f inside the FGH. Those are the ones that are denoting the functions inside. So now clearly this is in R3. There we go. So the vector field is the gradient of phi. And that's just simply, just get the three partial derivatives, plug them in, and you're done. So partial derivative in respect to x is going to be 6xz. Partial derivative in respect to y, first term dies. Second term is going to be negative 4. And then in terms of y, so that should be x, y, so 1 over x. So just 4 over x, negative 4 over x over here. And in terms of z is 3x squared. So this is just your phi x, phi y, and phi z. Partial derivatives, right? That's because we know that's what the gradient is. You had that on your exam last week. To find the gradient is the vector of partial derivatives. So whether it's fx, fy, fz, or phi x, phi y, phi z, it's all the same stuff, it's just different idea. I mean different, not different idea, different notation. And that's it. That's the vector fields, the basic idea of vector fields. Now we're going to take a short break. After the break, line integrals. Good luck.